On the 25th of December 2021, the National Aeronautics and Space Administration, NASA, with European and Canadian space agencies launched a rocket named Ariane 5 with a telescope as its payload. It took over 25 years with the involvement of more than 10,000 scientists and 14 countries. The total cost of this mission is roughly $10 billion United States dollars. What's special about this telescope? Let's find out. The name is James Webb Space Telescope, abbreviated as JWST, named after James E. Webb, who was the administrator of NASA from 1961 to 1968 and played an integral role in the Apollo program. This telescope is designed to provide improved infrared resolution and sensitivity over other space telescopes, and will enable a broad range of investigations across the fields of astronomy and cosmology, including observations of some of the most distant events and objects in the universe, such as the formation of the first galaxies, and allowing detailed atmospheric characterization of planets that may support life. Why infrared? Infrared waves have longer wavelengths than visible light, and can pass through dense regions of gas and dust in space, with less scattering and absorption. High redshift objects have their visible emissions shifted into the infrared. To understand what is redshift, let's listen to this ambulance sound carefully. This is called the Doppler effect. When the ambulance comes near us, we hear higher tone, and when it moves away, the tone gets lowered. This is because the sound waves are compressed and appears to our ears as high frequency. And the sound wave seems to be expanded when it moves away from us, so our ears perceived as lower frequency. Same thing happens to the light as well. When a planet or star moves away from us, the frequency of the light from it decreases, wavelength increases, so that it is now shifted from visible region to infrared region. This is called the redshift. Cold objects such as debris disks and planets emit most strongly in the infrared. When an object is not quite hot enough to radiate visible light, it will emit most of its energy in the infrared. Even objects that we think of as being very cold, such as an ice cube, emit infrared. Many objects in the universe are too cool and faint to be detected in visible light but can be detected in the infrared. Scientists are beginning to unlock the mysteries of cooler objects across the universe such as planets, cool stars, nebulae, and many more, by studying the infrared waves they emit. Why not a ground telescope? Ground-based telescopes must look through Earth's atmosphere, which is opaque in many infrared bands. Even where the atmosphere is transparent, many of the target chemical compounds, such as water, carbon dioxide, and methane, also exist in the Earth's atmosphere, vastly complicating the analysis. Why not an existing space telescope, like Hubble? Existing space telescopes such as Hubble cannot study these infrared bands since their mirrors are insufficiently cool. For example, the Hubble mirror is maintained at about 15 degrees Celsius, thus the telescope itself radiates strongly in the infrared bands. We just saw the importance of this telescope. Let's look at some of the basic features of it. The primary mirror. The primary mirror of JWST, the optical telescope element, consists of 18 hexagonal mirror segments made of gold-plated beryllium, which combine to create a 6.5 meters diameter mirror, considerably larger than Hubble's 2.4 meters mirror. Beryllium is a light metal, very strong for its weight, and is good at holding its shape across a range of temperatures. It is a good conductor of electricity and heat and is not magnetic. Because it is light and strong, beryllium is often used to build parts for supersonic airplanes and the space shuttle. Gold is used to improve the mirror's reflection of infrared light. The total amount of gold in the James Webb Space Telescope's mirrors is only 48 grams, less than 2 ounces. Optics. The optical design of JWST is known as a 3-mirror anastigmat. In this configuration, the primary mirror is concave, the secondary is convex, the tertiary is a concave mirror and it removes the resulting astigmatism and also flattens the focal plane. This also allows for a wider field of view. In addition, there is a fine steering mirror that can adjust its position many times per second to provide image stabilization. 3-mirror anastigmat was proven to have excellent features of correcting aberrations, wide spectral range, and shorter physical requirements. As a result, TMA telescopes have become more and more attractive, and have been applied in space projects to get clear images over a much larger piece of sky. The sun shield. To make observations in the infrared spectrum, JWST must be kept under -223.2 degrees Celsius. Otherwise, infrared radiation from the telescope itself would overwhelm its instruments. In the 5-layer sun shield, each layer is the size of a tennis court and as thin as a human hair, is constructed from Captain E, a commercially available polyamide film. Orbit. For keeping the telescope always at the preferred temperature, the orbit of the telescope is chosen as the Sun-Earth L2, Lagrange point, approximately 1.5 million kilometers beyond Earth's orbit around the Sun. A Lagrange point is a location in space, where the combined gravitational forces of two large bodies, such as Earth and the Sun, equal the centrifugal force felt by a much smaller third body. The interaction of the forces creates a point of equilibrium, where a spacecraft may be parked to make observations. YL2, objects near this Sun-Earth L2 point, can orbit the Sun in synchrony with the Earth, allowing the telescope to remain at a roughly constant distance, with the continuous orientation of its unique sun shield and equipment bus toward the Sun, Earth, and Moon to block their heat and light, and to maintain communications. The telescope is made to orbit around the L2 point instead of placing it exactly on the point. Scientists say, this is because it is easier to get there, avoid the sunshine getting blocked by the Earth's shadow, and avoid communication issues that could happen if the spacecraft is on the other side of the Moon, as the Moon itself blocks radio signals. Spacecraft bus. The spacecraft bus is the primary support component of the James Webb Space Telescope, which hosts a multitude of computing, communication, electric power, propulsion, and structural parts. Along with the sun shield, it forms the spacecraft element of the space telescope. Finally, let's watch a small illustration on how this giant telescope fit into the launch vehicle.